Hey math kids, let's work on the second optimization problem. Alright, so for this one, we have a 4-liter container, and we're told that it has a square base, which we're going to call all those sides x. Then it has vertical sides, which that drawing looks pretty bad, but you get the point. So we're going to call the height y. And so volume is length times width times height. And so our length is x, our width is x, and our height is y. And our volume is 4 liters. Now we want to eventually get these heights, and our goal is to actually get the lowest surface area while maintaining this volume. And so what we're going to do is we're going to use 1 liter is equal to 1,000 centimeters cubed. And so I'm going to change this to 4,000 using that. And then with some simplification, we get x squared times y. All right, so this is an equation that we can use in the future. Now, we're also going to look at the surface area because that's what it specifically is asking us for. And so these pieces around the outside are like rectangles that have a height of y and a length of x. And so if we do length times width, we get x times y. There are 4 of those around the outside, so we get 4. And then we want to add that to just the bottom, which is x times x, or x squared. Okay, so this is the surface area of the container. Okay, now what we're going to do, we're going to solve this for y. So we divide both sides by x squared. And so y is equal to 4,000 over x squared. And we're going to plug that in for y. We still have this plus x squared. This is still equal to our area. Okay, if we can cancel this with the squared down here, and then 4 times 4 is 16,000 over x plus x squared. And then we can rewrite that as 16,000 x to the negative 1 plus x squared. Now, because we're optimizing, so we need to take the derivative, set it equal to 0, and we're hoping to find a minima this time, because that's how we want to optimize it. We want the least amount of surface area, which means the least amount of material that we have to use. So we take the derivative of this. So a prime is going to be negative 16,000 x to the negative 2 plus 2x. Okay. And then we set the derivative equal to 0. So I'm going to switch that to 0. And to continue with this, I'm going to add this term over here. Okay. And I'm also going to switch this just to be 16,000 over x squared. These cancel, and that's equal to 2x. Okay, because x to the negative 2 is just x squared on the bottom. Multiply both sides by x squared. Those cancel, and so we get 16,000 is equal to 2x cubed. Divide by 2, we get 8,000 is equal to x cubed. And then if we cube root both sides, we end up with x is equal to 20. Okay, now we need to determine if that's a maxima or minima. And there's something we didn't talk about in the last video, but instead of doing a sign diagram or something like that to determine this, if you go in your book and you look at page 352 at the bottom, it states if our second derivative at a specific point is less than 0, then that's a local max. And if our second derivative at a specific point is greater than 0, we get a local min. Okay, so what we're going to do, we're going to take the second derivative of, second derivative of the original, but if we just take the derivative of this, that will give us the second derivative. And so let me just rewrite that. So we have negative 16,000 x to the negative 2 plus 2x. So we're going to take the derivative of that, which will give us our second derivative, and then we'll compare it to the second derivative rule, or the second derivative law, up there to help us figure out what's going on. Okay, so this is our first derivative. We take the derivative again, so it's going to be bring down the negative 2, that makes it positive, so it's 32,000 x to the negative 3 plus 2. And that's equal to the second derivative. And then we want to plug in our actual x value. So we're going to plug that in. 32,000 over 20 cubed. So I move this down to the bottom, it's x cubed. And then plus 2. All of these are positive. Positive over positive plus a positive makes it positive. And so we don't even need to simplify that. We know it's positive. And so since it's greater than or equal to 0, we do know that it's a local min. And so we do know that this is going to be our minimum optimization. Okay, so that's good. So we know that if we use x equals 20, that will give us the least amount of surface area. Now, they specifically want us to state the dimensions. Yes. So we need to look back at the top. And basically we can use this equation or this equation, and we just want to figure out, well, actually we don't know the area. So yeah, so we actually need to use this one. So we're going to use that one. And so it's 4,000, and then I'm going to plug in 20 for x. So we get 4,000 is equal to 400 y. Divide both sides by 400. 10 is equal to y. And all of that's in centimeters. So the base is a 20 centimeter by 20 centimeter square, and then the height is 10 centimeters. And that will optimize, that will give us the smallest surface area and still give us this original volume that was desired. Okay, the next video will show the next problem, and then we'll be done after that.